In an earlier video, we looked at the idea of two functions being inverses of each other, but we didn't have time in that video to go into all the little details of graphically and algebraically examining like all these different properties of inverse functions. So in this video, we want to take a look at just the idea of two functions being inverses of each other algebraically. So nothing to do with the graphs of these functions or anything like that, but in particular, I have two main questions I want to answer in this video. Number one is, how do we know if two functions are inverses of each other just looking at their functions algebraically, just the way they're written, without having to look at graphs and seeing if it's a reflection over such and such line or anything like that? How can we just look at the functions and tell if they're inverses of each other? And then number two, if somebody were to just hand us one function, how would we go about finding its inverse? So that's the two topics we want to take a look at in this particular video here. All right, so let's start with the first question here. How do we know if two functions are inverses of each other? Well, for that, let's go back to the basic idea of what an inverse function does. If you have an x value and you run it through some function, we'll call it little f, then your answer, your output, is f of x, obviously, as we all know. Well, what an inverse function does is you should be able to take that output and stick it in the inverse function, and if it really is an inverse, when you apply the inverse function to that value, the output value, then it should come back to the original number. Simple example would be like the square root function. If you take a number and square it, 5 squared is 25. But then if you apply the square root function to 25, it would come back to 5. And so if you were only restricting yourself to positive x values, this forwards backwards idea would work every time. So that would say that x squared and the square root function are inverses of each other for positive x's. Same thing like, if you had an x value and you added 4, and then you took that quantity and subtracted 4, then you would be right back where you started. Okay, so that's how we know if two functions are inverses of each other. So algebraically, how do we check this? Well, what we're really doing is when you take f of x and stick it inside f inverse, you're doing what's called composition. You're running x through both functions. And so if you can compose f and f inverse either way, right, either direction, and get x both times, then the two functions that you're looking at really are inverses of each other. Now, what happens if they're not inverses? Well, when you compose them, you'll get something simply other than x. That's the only difference there. Okay, so this is our algebraic way of testing to see if two functions are really inverses of each other. Let's try it with a simple example here. Let's say f is 3x plus 4, and g of x is x minus 4 divided by 3. They could be inverses. They both have a 3 and they both have a 4. One has a plus, one has a minus, but I'm not really sure at all whether these really are or are not inverses of each other. Now, just, as something extra, this is just something extra on the side here. Let's just see if we can take an intuitive guess as to whether they are. Let's just randomly just pick an x value. I'll say x equals 2, let's say. Well, if you plug in a 2 into f, 2 times 3 is 6, 6 and 4 make 10. So you plug in a 2, you get out a 10. Now, if these are inverses, what should definitely happen? Well, I think what should happen is, for g, when we plug in 10, hopefully we'll get 2, right? Because it's that forwards backwards concept. So let's try it. 10 minus 4 is 6. 6 divided by 3 really is 2. So AB has been swapped with BA. This gives me great confidence that these probably are going to be inverses, but I've got an important question for you. Just seeing that 2 goes to 10 and that 10 goes back to 2, is that sufficient to say that these two are definitely inverses of each other? Hopefully you said, no, that's not enough, because this forwards backwards idea has to work for every ordered pair on the function. And there's no way we could possibly test all of them. It's just impossible. There's too many x values. We would have to plug in to one function and then take that result and plug in the other. So I need to do it in a more algebraic nature. So I think they're inverses, but that's not quite good enough. So we're going to take f and we're going to compose it with g, meaning we're going to take g of x and stick it inside of f of x. Now, if you're not familiar with this notation, here's another way of writing composition. F of g of x. And this is a little bit more clear because you can see we're taking g and sticking it inside of f of x. So I'm going to take f here, which used to be 3x plus 4, but rather than the x, I'm going to insert g of x, which is x minus 4 over 3. Do a little algebra. The 3 and the divide by 3 cancel. X minus 4 plus 4. The minus 4 plus 4 cancel, and hey, we get x. That's great. Now, I'm not going to take the time to do it, but you should also take some time on your paper to check g of f of x. You do need to check these in both orders. Now, I'll go ahead and tell you, this is going to wind up being x. I just don't want to take the time to do it in this video, but you would do it in a similar fashion, just compose them the other way around. So that's it. That's our simple test to see if two functions are inverses of each other. We compose them and see if we get x. All right, number 2. Given one function, how do we find this inverse? And matter of fact, I actually did this before I started the video. I already knew that these were going to be inverses before I started, because what I did was I started with one function and then I went through a procedure to figure out who his inverse was going to be. So I wasn't really surprised when we got x here. It wasn't just like a shot in the dark. So how do you do that? How do you get one function and find its inverse? Well, it just goes back to that same idea again. If one function contains the point a comma b, then what's going to be the ordered pair for the inverse? It's going to be b comma a. And so if that holds true on like a point by point basis, why can't we just do it, with variable terms? And so here's a list of steps here that are going to help us walk through this concept of switching the x and the y. All right, so step 1 is if there's an f of x in your function, which typically functions are written with the notation f of x, get rid of it just temporarily and replace it with the letter y. They're the same thing. F of x is your y value. We know that. But just seeing the letter y will be less confusing than seeing f of x. Just trust me on that. Okay, and then step 2, here's kind of the key step here. We're going to take the x's and the y's and we're literally going to switch them. So everywhere there used to be an x, we're going to write a y, and everywhere that there used to be a y, we're going to write an x. And in effect, what that's doing is it's taking a point like AB and making it the point BA. That's in effect what we're doing. Now, there's one slight problem with that. Normally, your function will be y equals blah, blah, blah with a bunch of x's. But if you switch the x and the y, then x will be solved for, not the y. And that's kind of a problem. Normally, we like y to be solved for. So what we have to do, here's step 3. Once you've swapped x and y, solve for the y again. Now, the y is going to be embedded in your function because you swapped the letters, you swapped the variables. So it's going to take some algebra skills to get that y back. You might have to subtract things to the other side or divide them away, but just use your algebra skills to get that y isolated again. Now, once you've got that y isolated, you're pretty much done. Now, that y that we have currently, is that f of x like it was at the beginning of the problem? Actually, it's not, because after you switch the x and the y, then the y is actually f inverse now. So once you solve for that y at the very last step, switch the y back with f inverse of x because it'll be the inverse function then. Okay, let me show you with a quick example. Matter of fact, I'll show you with the one that we saw earlier in the video. All right, so here's f. So step 1, I'm going to do this kind of quickly. Y equals 3x plus 4. I'm just going to get rid of the y notation for a little bit. And this just makes it easier to look at. We have x's and y's. And so we're going to swap the x's and y's next. So x equals 3y plus 4. And then we're going to try to retrieve this y that's kind of stuck in the middle of our function now. So x minus 4 equals 3y. And so y equals x minus 4 all divided by 3. All right, so that's basically our answer. And forgive me for doing this so quickly, but just to speed things along, I'll just erase this y. I don't want to call that y anymore. I want to call it f inverse, because this is now the inverse function. All right, so there's f inverse. If I come up here and erase these two x values here, here is the original function, and that's how we get our inverse function from our original function.